So thank you very much for inviting me to present. So I've broken this down into a few sections. So one, this will start off with introduction, so there is some context to what I'm speaking about. And then I'll move on to talking about how we get access to patient data, what are the traditional approaches, and how we have improved upon it at Stanford. And with the goal of presenting why the new approach is both good for science and good for privacy. And then if I have some time left over, I'll speak to the challenges in healthcare research. A brief introduction about myself. Um, I started out as a computational physicist many years ago, worked for several years in computational drug design, moved to next generation sequencing, which was my first introduction to Stanford University. And then more recently working in biomedical data related research first with IRT, which is now TDS, the IT division for School of Medicine and Stanford Healthcare. So Stanford has a very thriving health research ecosystem, and it essentially comprises of the three entities here. So one is the university side, the School of Medicine, and then we have our children's hospital and the adult hospital. We are a research hospital, so a lot of our physicians are also research, they do active research. Collectively, we have at any time 3 to 4 million patients in our pool. There are 700 plus active research studies going on at any time with thousands of researchers. It's a highly multidisciplinary community. And then there are multiple stakeholders. So how research IT fits in this is we have, we have a team that provides services across multiple stakeholders. One of our primary role is to bring patient data from the two hospitals and make them available for research. And this is what I'll primarily focus on today. The second aspect is a lot of our research at the school involves doing new kinds of trials, new kinds of studies where in addition to the data that we already have from their hospital records, we are also trying to get new data for them. So this could be potentially in the form of data that comes in through surveys. It could be in the form of clinical trials. It could be in the form of mobile health data and so forth. And the last part of this is once there is an established research that has demonstrated good results, how do we take that back into the healthcare ecosystem? And in this entire process, we do many things. We advocate for our community, we partner with our community, we build solutions, we educate our research teams. So what makes the area of healthcare research interesting now is that we now have a huge amount of data in our healthcare systems. It is projected to grow to about 20 petabytes by year 2030. So this is not just the raw data that's at the hospital. The hospital data is going to be far larger, much larger. This is going to be the conservative estimate of the data that will be accessible to our researchers. And historically, it started out with electronic health record and radiology data. Now we have digital pathology data. We have things like bedside monitoring data. We have genomics data. We have things like you're computing your brain waves and so forth. So it's really a lot of really super cool data. So before I jump into the change that we have made, I want to first talk a little bit about our first generation clinical data warehouse. So this is the system that essentially brings in the data, the electronic health record data from the two hospitals and makes that accessible for research. So when you go visit the doctor, there is a system behind the scene that is tracking your diagnosis, the procedures that you go through. When you go talk to the physician, you tell them your family history. That all gets written down into what are called clinical notes. So these all get captured into this EHR system, electronic health record. And what we have at the two hospitals is the system called Epic. And the data we get from the Epic systems is a database called Clarity. And we also get these HL7 real-time data feeds. So our first generation clinical data warehouse was established in 2008. So it was conceived a little bit before the HITECH Act of 2009. And HITECH Act is what established EHR systems as the system of record for the hospital systems in US. Because we started way back then, ahead of when most hospitals even had EHR data, the data model that we picked ended up being very Stanford specific. And as the hospitals changed their EHR systems in time, they went from older systems to the newer system, which is Epic. The data model essentially stayed the same to provide a uniform layer for our researchers and kind of keep them distant from all the changes that were happening in the back end. So back then in 2008, we had about 10 gigabytes of data. Now this is closer to 4 terabytes of data. And there are thousands of researchers who are consuming this data right now. And the process they go through is they essentially go take a look at a web tool that allows them to make some queries based on statistical metrics. So they can go ask about how, in this particular case, how many people have a certain diagnosis, and they get an answer, in this particular case, 2,490. So based on that, then they decide if this is statistically relevant enough for the study they want to do. They go through this process called institutional review board. Then they get access to identified data. Then they start doing their analysis. So the fundamental issue with this is that they are using just the statistical data for estimating or designing their studies. And for any of you who has looked at, your Amazon web cart, you have a left-hand pane that gives you all the filters and the right-hand pane that gives you all the results. So here you have this particular example where if you're searching for red warm vest for women, you filter down, you say, okay, I just want the prime eligible, you can see 480 results. But if you take a look at your right-hand pane, very few of them are red vests and not relevant to what you're looking for. And this is actually a similar problem that happens in the biomedical space as well, because the data is noisy, it is complex, trying to do queries across them using just filters is exceptionally hard. So when you're designing your studies, if you just stick to filters, it's a hard problem. So now let's imagine a scenario where we can give people the data ahead of that IRB review, ahead of the hypothesis design stage. So what that looks like is instead of following the bottom row, they're following the top row where they're going to get access to the de-identified patient data. This process does not require an IRB. They develop their hypothesis using the de-identified data. The outcome is better science. And in many cases, you actually, particularly AI-driven cases, you do not require the institutional review board process. And in the end, you end up with better privacy because you're just working with de-identified data. So that's great. We can give people de-identified data. However, one of the biggest challenges we find is that 80% of the knowledge in our EHR system, in our healthcare system, is locked in those clinical notes. So this is, these are the pre-formed notes your doctor is writing when you're talking to your doctor. So for our 3 to 4 million patients, we have estimated 100 million notes that have significant content. So there are about 33 billion words, and de-identification is a challenge. So here, what I'm showing you in the figure is an example statement that a doctor will write and what information you can derive from this. So for example, the inflammatory bowel disease, this is a concept, it's a medical concept. What it's also telling you is that the patient has it as opposed to not having the disease. It tells you that the experiencer is a patient, not their family member. And the final thing that you learn from this is that it's happening at the time of your doctor's visit. It's not an event that happened in the past. So when you take a single note, a single note will have many, many words. Many of them will be medical concepts. You can actually break this down into many of these concepts that are happening to the patient at the time of the visit. And if you look across all our 100 million nodes, there are 2 billion concepts and 122,000 of them are unique concepts. So there is a lot of information that's there. So you could argue, what if I just present this level of data to the user and not show them the nodes? Then it boils down to back to the, the Amazon analogy, where they are not looking at the data, they are looking at synthesis of the data, and that often leads to poorer research quality. So we looked at all this in designing our second generation warehouse, and I'm going to now stick to that clinical notes as a concept, but you can actually extend the concept to other areas of biomedical data. So when we built our second generation data warehouse, it's called the OMAP Analytical Data Warehouse, and the data model comes from a consortium, and one of the advantages of having something from a consortium is it's a wider adoption of the database schema, how the patient is modeled in that. So essentially, if my data is in a common data model and Columbia University's data is in the same common data model, then a single query can run across both sites and you can actually do distributed computing. So we have a huge amount of data. We leverage the cloud compute capacity to de-identify, and we also use Google Cloud BigQuery to make the final database searchable. The final thing we do is we co-locate the data with a secure computational facility, which at Stanford is called it's a system called Stanford Nero Research Computing System. It's maintained by University IT. So let's come back to why are clinical notes hard to de-identify. So what you have is an example where you have in the original you have the patient's name, you have names of his daughters, Rosa and Iris. You also have the doctor's name, and the doctor's name happens to be not a PHI. It just happens to be an identifiable information. And then there is a procedure that happens on a particular date and so forth. So the first thing you do when you're trying to de-identify is you do a lexical analysis and you tokenize the words and you say, okay, this word is a name, this word is an address, this word is a doctor's name, this is a date, this is a social security number. You do that process, and there are multiple techniques for doing this. One is you already know this is your patient, you already have their known information, you know their names, you know their current address and so forth. So that's the known patient information. You can also leverage census data. So census data gives you things like addresses and zip codes. So you can go out and because it's possible that the patient has moved from address 1 to address 2, and some of the previous addresses are not there in the database anymore. But a census, looking at the census data will give you that address information. You can also do regular expression search. You can go in and say, okay, this looks like a telephone number, that looks like an email, this looks like an IP, and you can use that. And then the final heavy duty thing you can do is natural language processing, and that can help you do name entity recognition. So once you have tokenized, then the second thing you do is a mechanism that's called safe harbor, where you go and de-identify all these tokens. And and here you can use different levels of sophistication depending on what is your risk assessment for that particular workflow. So in this case, I think this is the most common case. What you do is you go in and you essentially redact. And the redaction can leave it in many states, but this is one of the more common states. You replace first names with F name, last names with L name. In this particular case, you could not identify Iris, one of the daughter's name, as a PHI. So that's leaked. So that's a leaked PHI. So there are two problems with this approach. One, this particular output, once you have this is no longer usable in downstream natural language processing, because any natural language processing algorithm is trained on something that looks like, a document. It could be, newspaper articles, it could be obituaries, it could be many sources, but it definitely doesn't look like this. So this particular output is really bad for your NLP research downstream, where you're trying to mine the data that exists in the nodes. And the other unfortunate thing is, if you're looking at this, the iris sticks out, and so does the 9/11 date. So it's really, really noticeable to human reader. It's perhaps not as noticeable to AI, because your original AI couldn't find the name iris in the first place. So the bigger worry is human reader can identify. So we run tokenization on our corpus, and we use multiple approaches. And what we are showing you here is that different entities. So, for example, benefit from different approaches. So the name benefits from patient lookup and a natural language processing, but the best way to get the MRN is again a lookup and regular expression search. And the other thing we find is names and dates are our two most common PHI, but there are many other PHI available in our nodes. So of the 100 million nodes, 22% have no PHI. Overall, there is 4% PHI in the nodes. So we discussed that the original safe harbor approach is perhaps not as good. What else can we do to make that better? So once you have tokenized, the next thing that can actually make your de-identification better is this method called hiding in plain sights. So what you do is you replace like with like. So a male name gets replaced by a male name. A female name gets replaced by a female name. Dates get, you identify a date, you can jitter them, you can replace a telephone number with another random telephone number, and so forth. The plus of this is that the output is now preserving all the features you might need for your downstream NLP. And the second thing is, you don't notice the leaked name, the name that we left behind, iris, is no longer noticeable in this data set. So excellent mechanism. This was actually the first came out from Vanderbilt, from Bradley Malan's lab. He's a privacy researcher. He has subsequently shown in his methods that 70% of the leaked PHI or PII is undetected by human readers under realistically aggressive attacks. So in these scenarios, the attackers are using all public information. They are doing searches on, the university information that's available. They're searching on the clinicians who are available, whose names are available. They're doing Facebook searches. So it's a truly realistic scenario. So the kind of things that get left behind in their algorithms are, where you have a formatting error. So in this particular case, Carol and MRN. So Carol is a name and the MRN is your ID in your hospital system. They are concatenated. And then there is incorrect capitalization. So in our context, for example, we actually handle the incorrect capitalization well, but there are other things we are working on. We are working on minimizing these formatting errors, minimizing spelling errors. We also find that our tokenization isn't as brilliant with ethnic names. We are also pulling in things that are preferred names so that we can do a better job in identifying our patient names. You can find more about this in our manuscript. And we use, as I mentioned, we use cloud for our analysis. So we start in BigQuery, use Cloud Dataflow for doing all of this intermediate work, and the output is again another BigQuery data set. Our total processing time happens to be 3 orders of magnitude faster than the fastest reported in literature. And the fastest reported in the literature also includes AWS Medical Comprehend. So if you think about it, we are doing pretty well in that realm. And in this process, we are booting up to process these 100 million nodes. We boot up 800 compute nodes. They churn away for 7 hours, cost us less than $450 to produce the de-identified data set. So you can clearly see that we couldn't have really done this without cloud. So what are some of the remaining challenges in healthcare research? So one is, data exists in silos. It's exceptionally hard to share data. So one of the tricks of the trade is trying to do network studies. And this is, again, bringing us back to the common data model that I discussed before. So common data model essentially puts your patient data in a common patient model in a common database schema is perhaps a easy way of thinking about it. So that way, it's, your corpus stays with you, your data silo stays with you, my data silo stays with me, but a common analytical query can run on both, and then we can aggregate the results. So this you're seeing here is essentially the same standardized study package goes to different sites. The sites submit their results back to the aggregated data result. And Stanford's OMOP recently participated in a COVID study. This was published in Nature Communications pretty recently. I think it was last week. One of the things we find that even though, yes, the common data model is making it feasible to do these kind of distributed studies, designing these studies is still hard, because even though you have done all the standardization, just because based on the kind of hospital you are, the kind of patients who come to you, the kind of area you are in, and if, particularly if you're in different countries, the standard of care, all of these things can make the data that exists in your database fairly unique. So what this is telling you, this graph that is showing you, is the uniqueness. So the first one, that is the really tall column here, that shows the number of concepts that are unique to one database. So what it requires is that when you're designing a query across your network study, this becomes not only a exercise in having really high quality data, it also becomes an exercise in designing your queries right. So the second thing I mentioned briefly before is that data sharing is rare, and you can understand that because none of this is truly de-identified, you can re-identify these patients relatively simply. There are not that many public databases around, so Mimic is one of those. And this came out of MIT Lab, and it's a huge, huge resource for our community. Since 2004, there have been 270 publications just using this data set alone. And Stanford's doing a similar thing in radiology, where we are pushing out these data sets to the broader community. And the vision is of ImageNet. So ImageNet has billions of images, perhaps millions or tens of millions of images that are nouns, that are specific to nouns, that you can use to train your models on. And this is the vision we have for our imaging data. And every single image is human reviewed prior to release. And the final point I want to make is privacy preserving queries is actually a very hard subject. So those of you who know Cynthia Dort's work, she's been working in differential privacy for a very long time. So she has this example where off the database, the data analyst is asking two simple questions. So the database essentially contains Nobel laureates and their flossing frequency. So how many living physics Nobel laureates floss regularly, and how many male living physics Nobel laureates floss regularly? Each individual question seems like it's privacy preserving. There could be nothing could go wrong. However, just based on these two questions, you can answer the specific question that does a particular Nobel laureate floss regularly. So if you want to hear more, I highly recommend you check out Cynthia Dork's talk at the Women in Data Science. She presented here at Stanford in 2019. Now, having said that, uh, these types of problems can be solved by differential privacy. And there is a huge amount of work that has gone in from Microsoft Research and differential privacy. And now they're in the process of creating a platform that can be more broadly used by the community. So I'm personally very hopeful of that. So I'm going to end there.